In this video, we'll look at Avogadro's number and the mole, one of the most important units in chemistry. Before we start that, I want to ask you guys a couple questions. When we're counting atoms, how many atoms are in a gram of carbon? Would you be able to tell from anything we know in the lab? Or how many atoms are in a gram of hydrogen? Do you think it'll be the same number of atoms as in a gram of carbon? Or how many atoms are in 12 grams of carbon? Would you be able to figure that out? All these questions are ones that we would want to know the answer to if we're doing a chemical reaction or an experiment. We want to know how much carbon we're actually working with or how much hydrogen we're actually working with. So for that, we do need to figure out how to count the number of atoms in a gram of carbon or the number of atoms in a gram of hydrogen and see if they're different from each other. For that, we're going to use Avogadro's number. Avogadro's number is a numerical value. It's the numerical value of a mole. And we define that as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So however many atoms there are in exactly 12 grams of carbon is Avogadro's number. This definition establishes a relationship between the mass, the grams of carbon, the stuff we can actually weigh out in the lab, and the number of atoms. So now we can relate how much mass we have to the number of atoms, and we'll know exactly how much atoms we're going to be able to use in our reactions. And so doing this and using this relationship, it allows us to count the atoms by weighing them. So now let's look a little closer at the mole. As I said, the mole is the amount of substance that contains the same number of atoms that there are in exactly 12 grams of carbon-12. We tend to call the mole like the chemist's dozen. If you think about a dozen, if I tell you had a dozen eggs, you know you have 12 eggs. So everybody knows that 1 dozen equals 12. Or if I told you we had 2 dozen eggs, you could automatically say, well, I have 24 eggs. Or if I said we had 10 dozen eggs, that'd be 120. Or you might have 10 dozen pennies. You know you have 120 pennies. So dozen is just kind of a unit we use to signify we have 12. We use the mole the exact same way, except in our case, a mole equals, 1 mole will equal 602 sectillion atoms. Now, trying to write it out like this, a little cumbersome. So we can really say 1 mole is 6.022 times 10 to the 23rd. And we have it as inverse moles because this is atoms per mole. So that way we can say 1 mole equals 6.022 times 10 to the 23rd. So just like the 12 here represents a dozen, 6.022 times 10 to the 23rd represents 1 mole. So that's why we call it the chemist's dozen, because it's a unit we use to signify a number. Just like with a dozen, we use that to signify a number. So let's look at this a little bit more. Avogadro's number is 6.022 times 10 to the 23rd of something, of anything. Could be atoms, you could do grains of sand on the beach, could do ants in an ant colony, trees on Earth, stars in the universe, planets in the universe. All of those could be measured by the number of moles. So I could say 1 mole of marbles, that equals 6.022 times 10 to the 23rd marbles. A lot of marbles there. Or even grains of sand. That equals 6.022 times 10 to the 23rd grains of sand. So 1 mole of anything, it doesn't matter what it is 6.022 times 10 to the 23rd. Just like if I said I had 1 dozen marbles, you know that equals 12 marbles. Or if you had 1 dozen grains of sand, you know that equals 12 grains of sand. It's the exact same idea. So it just means this number, Avogadro's number, is just corresponding to 6.022 times 10 to the 23rd of that number, of whatever it is you're counting. So thinking about it a little more, if I have 1 mole of anything, it's 6.022 times 10 to the 23rd of that thing. To expand it out a little more, the mass of 1 mole of a compound is what we call the molar mass. Or you can think of the units as grams, the mass, per mole. So that means lighter compounds weigh less. They have a lower molar mass. So let's think about this. Which one weighs more, 1 mole of uranium or 1 mole of gold? You may be telling yourself, I have no clue. I don't know how much a mole of either one weighs. How can I figure it out? Well, if we look at the periodic table is our friend here. So if we look at the periodic table, uranium has a mass of 238 atomic mass units. So 1 atom of uranium weighs 238 atomic mass units. Gold has an atomic mass unit of 196.97. That means each gold atom weighs a lot less than each uranium atom. And if in both cases I have 6.022 times 10 to the 23rd, that means that the uranium is going to end up weighing a lot more than the gold. Because it'd be the same as if you were trying to compare 2 5-pound weights versus 2 3-pound weights. If I had the 5-pound weights, that would add up to 10 pounds total. If I had the 2 3-pounds, that'd only add up to 6 pounds. But they're both still weights, just like these are both still atoms, but 1 atom weighs a lot more. So that means 1 mole of uranium is going to weigh more than 1 mole of gold. Let's ask another question. Which one has more atoms? 10 moles of magnesium or 10 moles of sodium? Well, we know that magnesium weighs more than the sodium. Magnesium has an atomic mass unit of about 24.31. And sodium is 22.99. So obviously the magnesium weighs more per atom. But now we're asking to count how many atoms. We're counting the number of atoms. We don't care about the weight. So since we're counting the number of atoms, I have 10 and 10. So that means neither one. They both have the same number of atoms. They both have 10 moles of atoms. It'd be like asking the same question, which one has more atoms, 10 dozen pieces of magnesium or 10 dozen pieces of sodium? You can see how using mole and dozen, you can interchange them because they're just a way to represent a certain number. So now looking a little closer at this molar mass idea, this grams per mole, that unit we were looking at earlier. The molar mass of a substance is the mass per mole of its entity. So the mass of the atoms, the mass of molecules, or the formula units. That's what the molar mass is. So the mass in grams of 1 mole of atoms or compound equals the molar mass, the grams per mole. And the beauty of the periodic table is that that number that we've been using for atomic mass units, that's going to be the same number we use for molar mass. Because the way they came about the definition for both of those was using carbon and using a similar method for carbon. So if we remember earlier, the definition for an atomic mass unit was 1/12 the weight of one carbon-12 atom. And the definition for a mole is the number of atoms in 12 grams of carbon-12. You see how we're using carbon-12 for both of them? So now we can relate the atomic mass units to its molar mass. So that means one atom of magnesium, if I look on the periodic table, is about 24 atomic mass units, which means 1 mole of magnesium is 12 grams of magnesium. So now I can use Avogadro's number to correlate between the mass of the atom and the mass of the mole. So when we're looking at a periodic table, and if I use hydrogen, that number we see on the bottom there, that we know is the atomic mass unit. It is also our molar mass. It is also our grams per mole. So really we use that number. If we're looking at individual atoms, we use it as an atomic mass unit. If we're looking at as the amount of substance we might weigh out in the lab, then we can use grams per mole. But it's still the same number on the bottom. That's the beauty of the periodic table, is we have all this information contained in simple little squares like this. There's so much information we can get out of that. And that's because for both, as I said, for both of them, they use carbon-12 as their standard to figure it out. So looking at our relationship with our moles, if I look at glucose, glucose is C6H12O6. So looking at that formula, I can get all of this information here. Looking at that formula, I can tell there's 6 carbon atoms because there's a 6 here. Because now I know the relationship between atoms and moles, that means I have 6 moles of atom. I'm going to have 6 moles of carbon atoms. And if I want to figure out the relationship of atoms per mole, it'd be 6 times Avogadro's number. If I want to figure out the mass of the carbons, it's 6 times the mass of a carbon atom, 12.01. If I want to figure out the mass in grams, I can figure it out. It'd be 6 times that 12.01 would give me 72.06 grams instead of atomic mass units, because it's still the exact same number. Just depends if you want to look at the atomic scale or the macro scale. We can do the same thing for hydrogen and oxygen. So really, this one is when you look at the atomic scale. And this, I kind of like to say we're looking at macro, or it's laboratory scale. Because on a scale, we can actually see 12 grams. I can definitively weigh out 12 grams on any sort of scale in the chemistry lab you might see. I can't weigh out 12 atomic mass units. Remember, atomic mass units are times 10 to the negative 20 something. We can't weigh that out. But 12 grams, I can weigh out 12 grams. And we can do the same thing for the oxygen. So all of this information is contained within just this formula. I can figure out all of this. And we can use this to figure out a relationship between the amount of glucose and some other molecule we might be using. And so now you guys should be able to use Avogadro's number and understand a little bit about Avogadro's number and how it relates to the mole, and also how we can go from the atomic scale into the macro scale, into the laboratory scale. And we're going to start using the mole when we do our calculations for stoichiometry